Well, welcome to another big review video, and we're going to follow up our big night with related rates last night with another big one, a big topic called optimization. It's another application of the derivatives, and you could easily see how it could be very useful in the real world, especially in an engineering field. But a couple of real basic ideas here. Our first definition that we want to get in is that a maximum or a minimum of a function occurs at a point where the derivative of that function is 0. Or there is one other particular case where the derivative fails to do what? Fails to exist. Okay? Now basically what we've defined here is what I call a critical point. Okay? This is where we find critical points for a function. It's whenever the derivative is equal to 0 or when it fails to exist. And then the big one here, and I think this is the one that has even more meaning going into today, it says, at a point where the first derivative equals 0, two things could happen. Either the curve had, well, here's the one that we do know for sure, that the curve has a horizontal tangent line, okay, at which it could be reaching a peak, which is referring to a maximum point on that graph, a relative max, or it could be approaching or reaching a valley. Alright, which of course refers to a relative minimum. So what we've got here is we're kind of picturing a well-behaved graph that looks like such. We've got a horizontal asymptote right there. We've also got one right here, and you could see how we could easily have a max or a min. Alright, I got two examples picked out for tonight, and let's go ahead and jump into them. Okay, our first example describes a rectangle that is to be inscribed in a semicircle with a radius of 4, with one side on the semicircle's diameter. What is the largest area this rectangle can have? So this is one of those sneaky ones. I've seen a lot of times where students they stop a little too early, and trust me, this is a great multiple choice question, and the AP wisely makes one of the choices that intermediate answer, where you basically find the x value that produces the smallest or largest rectangle, and we just want to make sure we actually, when we're all said and done, we're going to have the area of that said rectangle. Okay, what kind of semicircle are they describing? They're describing one that, let's assume that it's centered around the origin, and it looks like this. We've got a radius of 4, and so I'm going to say that this equation here, the top half, is radical, let's see, 2 squared, which is 4 minus x squared. So that's the equation of that top half. Now what we need to do is we need to inscribe some rectangle that's resting on the diameter, aka the x-axis, and we're going to kind of have this happy medium. I mean, you could imagine we could have a really tall, narrow one. We could also have a really wide one, but it wouldn't be very tall. So we're trying to think of all the possible rectangles that could be inscribed within the semicircle, which one's actually the biggest. So our next goal is to try to represent the area. Now the distance, let's say that this ordered pair up here is kind of a mystery point right now. It's x comma y, that vertex. So it says this distance right here is x units. The height of that rectangle is y units. So really the base has a total measure of 2x, and the height has a measure of y. Now actually, this is a well-known shortcut that I'm going to take advantage of. I'm actually going to kill the 2. Okay, and the reason I get away with that is what I'm going to do is I'm going to maximize the biggest rectangle in the first quadrant, and then right at the very end when I'm all done, I'm just going to double that answer to get the area of the entire one that contains both the first and second quadrants. So anyway, the area of the one rectangle in the first quadrant is going to have a base of x and a height of y, and I want to express the area in terms of just one variable, so I'm going to say x radical 4 minus x squared. Now that we've expressed area in terms of just one variable, I'm now ready to take that derivative and set it equal to 0. The derivatives here today, unlike yesterday, are with respect to the independent variable, and that's worth putting a little asterisk in your notebook. The derivative is not with respect to t, it's with respect to whoever your independent variable is, and in this case, it's x. So dA dx, or just a prime here. And I'm going to jump into the product rule. Try it on your own. Come on back, see if you got the same thing I did. Oops. First of all, a little typo I caught as I was starting to do that derivative. The radius was 4, so I should have a 16 minus x squared in that radical. So go ahead really quick, and if you hadn't caught that already, hopefully you were scratching your head wondering what the heck was wrong with me. You can go ahead and change your 4s to 16. But basically, I went through my product rule here, I've got the first times the derivative of the second using my right chain rule, plus the second times the derivative of the first, which was just a 1. Now as I start to clean this up a little bit, I've got a prime is really negative x squared, the 1/2 killed the 2 there, all over this radical, and plus this radical. And all I'm going to do now is set this radical equal to 0 and try to solve for x and figure out what my critical point is here. So let's see, go ahead again, good time to hit the pause button, come on back, see if you got the same critical point I did. Okay, first thing I did was I grabbed this term right here and added it to the other side, and then I cross multiplied. That was beautiful because it killed the radical on this side here on the left. And I got a really nice critical point of, actually it was plus or minus radical 8, and I just grabbed the positive value there. And now I need to do, and of course you could reduce that and call it 2 radical 2 if you wanted to. If it's a free response question, we are going to have to generate a sign chart here. Endpoints of 0 and 4, critical point of 2 radical 2 or radical 8. Okay, we're going to plug into a prime. I plugged a 1 into that a prime and got positive, and then I plugged a 3 in and I got negatives. And so we just proved that the area is going to gradually increase as x increases from 0 to 2 radical 2, and then the area is going to decrease as x increases from 2 radical 2 to 4. Now, and this is the kind of caution to the wind that we threw out earlier, is we're not done yet, and radical 8 or 2 radical 2 will be one of the choices on the multiple choice exam. We want to now figure out what was the area at that particular moment. So I'm going to scroll back up here to the top, and I'm going to look at my diagram, and I'm going to ask myself, okay, now if the x-coordinate was radical 8, all right, we're going to say x is radical 8. What is the corresponding y-coordinate? Let's see, I'll plug it into right here. That's 16 minus radical 8 squared. I think I just got radical 8 again. So both the x and the y coordinates will be radical 8. That's the ordered pair that corresponds to this vertex up here. And the area would then be just a beautiful 8. So, now, oops, and one more trick. That only describes the area in the first quadrant. So the area of this entire rectangle right here is going to be 16. So an area of the biggest inscribed rectangle would be 16. All right, one more to go. Well, the bad news is, if you thought the last one was messy, wait till you see this rascal. And I'll tell you what, these problems are always very doable, but they do take time. And usually if I do see this on a multiple choice, I'm tempted to kind of skip it initially and then just come back to it once I finish all the other problems, because there are a lot of other problems that are earn you just as many points, but they're quicker and easier to do. So, but anyway, let's go ahead and get started here. We've got this, they've described this very basic circle centered at the origin with a radius of 1 this time. And they said, hey, I want to find the point on that circle that is the closest to this other point, 2, 1. Now remember, that's 1. So I'm going to go over another unit here, about right there, and go up to a height of 1. So here's my point, 2, 1. So there's some mystery point on that circle, and I'm going to guess that it's about right there, that I think is closer to the point 2, 1 than any other point on that circle. And that mystery point, I'm going to give him a name. I'm going to call him x, y. So what we're going to do is we're going to try to minimize the distance between these 2 points. I want to try to come up with an expression for distance, and then we're going to minimize that by taking the first derivative and setting it equal to 0, or asking ourselves when it doesn't exist. So the distance between those 2 points, we'll say, is the square root of x minus 2 quantity squared plus y minus 1 quantity squared. The slight problem here is that distance is being expressed in terms of 2 variables, and that's a big no-no. So I'm going to try to see if I can substitute for that y. Now, the equation of this upper half is going to be, let's see, y equals radical 1 minus x squared. So that's the expression that I'm going to substitute in for y right there. And I've got the distance is really x minus 2 quantity squared plus, look at this, radical 1 minus x squared minus 1 quantity squared. Okay, now that you have a choice here, and I don't know if one's clearly wiser than the other. We could do the derivative right now, but we would just have gobs and gobs of chain rule to work our way through. The other option is, and this is the one that I'm going to choose, is I'm going to go ahead and FOIL out everything inside and clean up the inside of that radical the best I can, and then I'm going to invest my energy in the derivative. So right now, my derivative's going to, let's see, the first one FOILed out is x squared minus 4x plus 4. Okay, and then the second one's going to be, let's see, radical times itself is just going to give me 1 minus x squared. Then the outer and the inner combined will give me negative 2 1 minus x squared radical plus 1. Okay, if we combine some like terms, I think those x squareds are going to cancel. I think I'm going to get 6 minus 4x, and then the minus 2 radical 1 minus x squared. Okay, well, the bad news is it didn't get super clean, did it? So now we're ready to invest our energy in this guy's derivative. I'll switch colors here. The derivative is with respect to the independent variable, which in this case again is x. That was quite convenient, eh? Chain rule says 1/2 inner function 6 minus 4x minus 2 radical 1 minus x squared. Raised that new exponent to negative 1/2. Now here's where it gets really interesting. We got negative 4. And then I'm going to start doing some chain rule. I've got negative 1 minus x squared to the negative 1/2 times negative 2x. All right. To clean this up just a little bit before I set it equal to 0, I think basically this entire expression here is going to be my numerator. So I've got, let's see, negative 4 plus 2x over radical 1 minus x squared. And that's all divided by the 2. Okay, this 2 right here went on the bottom. And then I've got a long radical, 6 minus 4x minus 2 radical 1 minus x squared. Okay, pretty disgusting, huh? Well, we're going to set that derivative equal to 0. And when we cross multiply, here's the exciting news. And this should happen every time you do the derivative of a distance formula. Everything that used to be inside, okay, by the time we cross multiply, this sucker's going to die, because it gets multiplied by 0. So we really have negative 4 plus 2x over radical 1 minus x squared is equal to 0. We'll go ahead and we'll add the 4 to the other side. Alright, so we've got 2x over radical 1 minus x squared is equal to 4. 2x is equal to 4 radical 1 minus x squared. Let's see, that barrier divides into there, gives me a 2. I'm going to square both sides now, and we get x squared equals 1 minus x squared. Oops, I think I just forgot about the 2 that was on the outside. That 2 that was right here becomes a 4. So now all I'm going to do is distribute the 4 and then add, let's see, then we'll just combine some like terms. 4 minus 4x squared. 5x squared equals 4. X squared equals 4/5. Man, some really intense algebra here, huh? Took the square root, I got plus or minus 2 over radical 5. Again, I'm in the first quadrant, so I'm going to automatically reject that negative value. Again, if it's a free response question, we're going to generate a quick sign chart here. I said the possible x values were between 0 and 1. 2 over radical 5 falls in right around there. We'll plug it into d prime. And again, I'm really just worried about the numerator of d prime, and we got a bunch of negatives here when I plugged in a really small number, and then we got positives here, so the distance is decreasing and then increasing. So the distance is minimized when x equals 2 over radical 5, and I just want to scroll back up and see what they actually asked for and just make sure we answered their question completely. Let's see what we got here. Okay, they said find the closest point. So they are actually asking for the entire point. I need the entire ordered pair of that blue dot. We already know that x is equal to 2 over radical 5. So, and it falls on the curve, so I'm just going to substitute it into this expression right here. 1 minus 2 over radical 5 squared. That's going to be, let's see, 1 minus 4/5, which is really 1/5, which turns out to be 1 over radical 5. So at the end of the day, when the dust settles, I'm going to say the ordered pair 2 over radical 5, comma 1 over radical 5 is the point on the unit circle that is the closest to this random point 2, 1 on the outside. So there's a couple of intense optimization problems, one where we maximized, one where we minimized, and I hope you're ready to roll tomorrow.